Quantum computers, they're this incredible promise, right? The ability to solve problems we once thought were impossible. But there's a catch, a huge one. The very heart of these machines, the qubits, they're ridiculously fragile. I mean, the slightest little nudge from the outside world can just, poof, wipe out all their information. So how on earth do we protect them? Well, it turns out, and this is the really cool part, the best way to fight quantum problems is with, you guessed it, more quantum tricks. All right, let's get into it.
So, here's our game plan. First, we'll talk about this fragile quantum dream. Then, we'll look at an old trick we use for regular computer bits. After that, we'll see exactly why that simple trick just completely falls apart in the quantum realm. And then we'll get to the main event, the quantum fix itself. And trust me, the price of that perfection is pretty staggering.
All right, first up, a fragile quantum dream. Let's really set the stage here. The potential power of quantum computing is just mind-boggling, right? But it's all built on this one fundamental challenge, this one giant hurdle. How do you keep the quantum information from just disappearing?
You know, the physicist Asher Paris put it perfectly. He said, "Quantum phenomena do not occur in a Hilbert space, they occur in a laboratory." And what he meant by that is, it's easy to write down these beautiful, perfect equations on paper. But in the real world, in a lab, qubits are physical things. They're messy. They're constantly getting bumped and jostled by the world around them.
And hey, you don't have to take my word for it. Just look at this. On the left, that's what's supposed to happen. This is a quantum search algorithm running on a perfect simulator. See that sharp peak? Bam! That's the right answer, clear as day. Now, look at the right. That's the same algorithm run on a real 5-qubit quantum computer. It's just a mess, right? A flat line of noise. The answer is totally gone, just lost in all that static.
This chaos, it has a name. And in the world of quantum computing, it's the ultimate villain. It's called decoherence. It's basically the process of all that precious quantum information just leaking away, getting tangled up with the outside world until it's lost for good. And make no mistake, this is the #1 biggest obstacle we face in building a useful, large-scale quantum computer.
Okay, so the problem seems massive, but, dealing with errors in computing isn't a totally new idea. We've been doing it for decades. So before we dive back into the quantum weirdness, let's take a step back and look at a simple, old trick we use for the regular bits in the phone or laptop you're using right now.
So the classical solution is actually kind of beautiful in its simplicity. It's all about redundancy. Let's say you have a single bit of information you want to protect, a 0. Instead of just storing 1 0, you make a few copies. You store it as 0 0 0. Now, let's say some random noise comes along and flips one of them. Your 0 0 0 becomes 0 1 0. Well, now it's super easy to spot the error, right? You just take a majority vote. Okay, I've got 2 zeros and 1 1. The 1 must be the mistake. You flip it back to a 0 and boom, you're back to 0 0 0. Your original information is safe, simple, elegant, problem solved.
Okay, that seems easy enough. So why can't we just do the exact same thing for qubits? Well, this is where the quantum world says, not so fast, and throws a giant wrench into our beautiful, simple plan. It plays by a completely different and much, much weirder set of rules.
So let's just ask the obvious question head on. Why can't we just, copy the quantum information? Just take 1 qubit and make 3 identical copies, just like we did with the classical bit. It seems like the most logical first step.
And here's the roadblock. It's a big one. It's called the no-cloning theorem. And it's not a guideline. It's a fundamental law of the universe. It states that it is impossible to create a perfect, independent copy of an unknown quantum state. There's no copy and paste for qubits. You just can't do it. And right there, our entire classical strategy just goes right out the window.
And oh, it gets worse. That's just problem number 1. We're actually facing a triple threat here. So first, the no-cloning theorem. You can't copy a qubit. Second, quantum errors aren't just simple flips from 0 to 1. Oh no, you can have phase flips and all sorts of other errors on a continuous spectrum. It's way more complicated. And third, and this one is a real mind-bender, the very act of looking at a qubit to check if it has an error destroys its special quantum state. So how can you fix something if you can't even look at it without breaking it? It sounds impossible.
So let's recap. You can't copy the data, there are tons of different kinds of errors, and you can't even measure the data to check for errors. It seems like we're completely stuck, right? Well, this is where the real genius comes in. The solution is to take all that quantum weirdness that's causing the problem and use it against itself.
Okay, so if we can't copy the information, what can we do? The first key is a property you've probably heard of,
Entanglement. The idea is, instead of trying to make 3 separate copies, we can take our one precious qubit of data and entangle it with a few other helper qubits. By doing this, the information isn't copied, it's smeared out, shared across all of them. They become a single collective unit, a logical qubit, without breaking the no-cloning rule.
This leads to this really elegant 4-step process. Think of it like a clever plan. Step 1 is encode. You entangle your main data qubit with some helper qubits, spreading the information out. Step 2 is detect. And this is the really magical part. You use special quantum gates to check for disagreements between the qubits, but, and this is key, you do it without ever looking at the actual data. You're not asking, are you a 0 or a 1? You're asking, do you guys all still agree with each other? Step 3 is decode. The answers to those questions give you a little code, an error report called a syndrome. And finally, step 4 is correct. That syndrome tells you exactly which qubit has an error and what you need to do to fix it.
This syndrome is the secret sauce. It's brilliant. It's like a decoder ring. If the syndrome comes back as, say, 01, that doesn't tell you anything about the secret quantum information stored in the qubits. Not a thing. All it tells you is, hey, qubit number 3 has an error and you need to apply this specific fix. It's an error report that points to the problem without revealing the message. It's how we fix the mistake without ever opening the envelope.
So there you have it, a solution. It's incredibly clever, it uses quantum mechanics to solve a quantum problem, but, and it's a big but, it is incredibly, incredibly expensive. The price for this kind of perfection, for this stability, well, it's staggering, and it's paid in the currency of qubits.
Remember how I mentioned that quantum errors are more than just simple bit flips? Well, that simple example we walked through was designed just for bit flips. But in the real world, you've got to worry about phase flips and combinations of the two, and even other weirder errors like amplitude damping. It's a whole zoo of things that can go wrong. A truly useful error correction code has to be able to handle all of them. So what does that complexity mean in practice? It means you need a lot more of those helper qubits to build just one single, stable, fully protected logical qubit, one that can withstand all those different types of errors. Some of our best-known techniques require, get this, 49 physical qubits, 49 real qubits just to create one reliable one. That is a massive overhead.
Now, this might sound like science fiction, this idea of needing millions of qubits, but it's not. This huge engineering challenge is exactly what the big players in the field are focused on right now. Companies like Google, IBM, and others have published these detailed roadmaps, and their goal is to build machines with thousands, then tens of thousands, and eventually millions of physical qubits. Why? Precisely to pay this overhead cost. They need enough qubits to both run the error correction and have some left over to do useful calculations.
So that's really the takeaway here. You can think of quantum error correction, or QEC, as this absolutely essential bridge. On one side of the canyon, you have the noisy, error-prone devices we have today. On the other side, the powerful, world-changing quantum computers we dream about. QEC is the bridge we have to build to get from here to there, and it's going to be a huge, resource-intensive construction project.
And this whole thing leaves us with this fascinating paradox, a real chicken and egg problem to chew on. Think about it. We need error correction to make a quantum computer work reliably, but we need a really big quantum computer with tons of qubits just to make the error correction work in the first place. So, how do you solve that? How do you break that cycle? Well, figuring that out is probably the single biggest challenge in quantum computing for the next decade.